Okay, I think we can start. Okay, we're to introduce Larry, who will tell us about Springer theory and KLR algebras from quiver varieties.
Okay. I guess. Okay. So last time, we saw the convolution algebra. Sorry. So for today, okay, so we saw the convolution algebra of this thing, the G equivariant homology of what is it? Borel cross Borel, as it, and we saw by like how it acts on convolution on here. And that, I mean, we know that like this is, well, via induction, this is HT star of X, which is like it, so it has like, so as a what is it? As a or as a module over as a module over like the symmetric algebra of like T dual. It's just like indexed by like the Weil groups. Yeah. Or like these B orbits. So and then so as algebra, Bingzi told us last time, it was like generated by these things called like it's like DIs. Like where like let's call them the SIs, or like SI being a simple root. And the way they commute with just like polynomials in like T dual is DSI times F in sim. I believe minus SI, like the Weil group acting on these T dual, on like DSI equals to DSI of F, as they say, which ended up being the action that's given here, which is SI acting on F minus F divided by the roots A sub I. Right, so that's what we did last time. And let me just make a remark, slash example that will become motivated later, which is the case of GLN. So if we let like C y1 dot 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 yn be, you know, the roots, and then let, well, I guess integral roots, and then let and have simple roots AI being yi minus yi plus 1, then pictorially Neo-Hacker algebra. I should start a new board. Yeah. Then Neo-Hacker algebra, at least for like G equals GLN, is generated by these like pictures that like look like these with like crossings and like dots inside, like crossings and dots, where like this stands for yi, and like this crossing stands for these di's, and then so this becomes like this this module generated by these graphs mod relations that I don't remember off the top of my head, so I'm gonna have to pull it up. Well, one of them is this equals 0. What's the rest? I think something along the lines of like this one minus, please correct me if I'm wrong. This one is this one, which is also this one minus this one. Yeah. And I think there's another one that looks like this one equals what was I trying to say? Yeah, like what did that look like? Is this right? I think these are all the relations.
I think one goes to 3 on the right, but to the 2 on the left, but
You want 3 crossings for the
I'm sorry.
young bits.
It looks something like okay, that's better. Okay, so these are all the relations. So pictorially, it will look something like this. I bring this up because later we'll see the KLR algebra, which will also be kind of like similar, like kind of pictorially defined. Okay, so I'm going to wrap up like the recollection here. Can I use this board or stick to this board?
and just minimize the number of times you move.
Okay, I'll do my best to stick to this board then.
No, just like use the boards and other boards.
I'm sorry.
I mean, oh no, please don't erase it. Sorry, you can. First priority is not erasing, second is moving less.
Okay, got it, understood. Okay, thank you. So I'll use as much of this board before moving then.
Yeah.
Okay, today's plan. So one is to like generalize and give convolution algebra structure on this thing I'm going to write, whatever that means. Yes. Something that looks like this. And then give some examples. Two particularly important one. This one is like the Grothendieck spring resolution. And the other one is, as I mentioned, KLR, Khovanov-Lauda-Rouquier algebra. Okay. Now I move. Yes.
How do you read actually the picture?
That's this one. Yeah.
And you read top to bottom.
Yeah, top to bottom, and you concatenate top to bottom. Yes. Yes. Okay. Next thing to do. Yes. Definition or like construction. Let G N be some G rep. B, sorry, and then U inside of N, where U is B stable. Then this thing, again, this is the flag. This is a vector bundle over X, or over like the phi variety. It is something that looks like this: B mod B in the Cartesian product, such that B is in G translation or like action on U. Okay, so this is this is vector bundle. Fiber over GB is GW. Cool. Let's give some quick examples, or like rather like a important class of examples. So one very common way we construct this, fix a representation N, and then choose some gamma in the what's that name? It's like the torus Lie, no, not the torus, like the Lie algebra of the torus. Yeah. Such that for all positive roots, AI of gamma is real, and it is greater than 0, so it's positive. Okay, so take a element in the why am I blanking on like what's the name of it?
Co-character maybe is what.
I'm sorry. Yeah, co-character. Thank you. Yeah, co-character that is positive all the time, with like positive roots. Then and define U sub gamma to be the sum. So we decompose into weights of call it n, yeah, lambda, such that lambda of gamma is non-negative, right? So this is preserved under the Borel, right? Because the Borel will only kind of raise the weight. So, yep. Okay, so example. N being G with the adjoint action. Then, well, for any gamma where AI gamma is greater than 0, well, U sub gamma is just the upper Borel. Good.
So like,
Yes.
U gamma is like lambda gamma and it's still under here.
Yeah, so I only so if I decompose this into like weight spaces.
Yeah.
Okay. And then the other example is quiver representation. I'll talk about this later. Okay, so now okay, so now in general, so question, what is convolution, or like what is H star of whatever X U tensor quiver over N X of some U prime, or more generally, this direct sum. Find in some set as convolution algebra. So the way that we will do this is basically the same way Mingxi did for us last time. Look at these things like action on this space via, well, convolution. So I guess I like to think of these kind of like as like matrix multiplication. So action of something on in here would probably like send something from, this is prime, so something from my x of like xu prime to the cohomology of xu. But I'll do my best to make it more precise later. Okay, so let's do an easy case.
So here we're not doing the equivalent.
Oh, what am I doing? No. Sorry. Thank you. Okay, easy case. N is, or rather, H, G with like the same U's on both sides. Where actually U is G stable. Okay, so usually, like in general, we require that U be B stable, but if it's G stable, what happens, right? Then well, this is like GB, G prime B, and like some small u, such that like U is in big U intersect G times big U. But then if we assume it's stable, that's just U. So this is just the flag times flag times this representation. Is that right? It's a vector bundle. Yeah, so being a vector bundle, it should have isomorphic equivariant homology as flag times flag, which we did last time. So this is kind of the easiest case, and kind of like why, like, I guess why this is a generalization, like what I'm doing today, of the nil-Hecke algebra from last week. Okay, so in general, so observe that if we take, let's see, so if we take x sub u by the product x sub u prime projecting onto x cross x, then pi restricted to each g orbit in the bottom is vector bundle. So this is a vibration, is my point. So the well, isotropy group of O sub W is B intersect B conjugate by W, and this is associated bundle of the rep of U intersect W acting on U prime. Well, but I guess it's enough that we know it's a vibration. So let's see. So if it's a vibration, yeah, so it's also generated, or rather, sorry, H star x u tensor n x u is also equal to like C with like polynomial in the co-root, and I guess my inverse of the pullback is a better word. Of these classes as a vector bundle. Is that okay?
Sorry, Larry. So sorry, I didn't quite follow. So what is OW here?
So OW, this is G orbit in the flag times flag of the element EB WB.
Oh, okay. So, and what is the notation on the very top? Is pi restricted to what?
Like restricted to like this, like the invert, like the
I mean,
like
on the right, I just couldn't read the notation. I mean, since the camera is not that clear, so what's the notation? What inverse OW?
pi inverse.
Okay, okay, I see. So,
Yeah, so it's a cellular vibration.
I see. Thanks.
Mm-hmm.
U is defined on the other blackboard, which is not currently showing. We take fiber product.
Thanks.
Okay. So let's see what's happening.
Do you pick two different U's?
Yeah. In general, I'm allowed to pick the two different U's because both of them sit inside. They both sit inside this grep n. Yeah. Okay. So I guess my point is that so I guess my point is if we can generate like each of these things, then we're good. Unfortunately, I don't know how, but I'm going to give a few generators. Of so A sub S being, so in general I say like U prime in this subset S. How do I keep on forgetting my G's? It's a G equivariant of XU times XU prime. This direct sum. So first kind, these are what I call or what Ben Webster called RU prime. So what is this? This is the I think this is the class of pi inverse of O sub E, which is equal to the diagonal in flag times flag. Yes. And yes, sorry.
Maybe so. Is the spy a direct sum? I mean, like what is the domain of line?
Domain is well, this one
Yes.
XU times n XU prime to x times x.
RU prime. Okay, well, yeah, maybe just okay. Maybe at some point it would be helpful to write PUU prime so that different maps are denoted by different letters.
Okay, I'll do my best.
Yeah. No
It has some like specific.
Sorry, where did I write S? S for now for now it's just like arbitrary, I guess.
I think fine.
Yeah, it should be finite. But I guess the thing is, yeah, it's finite. It's finite. Yeah, let's say it's finite. Okay, so also, well, pi inverse of this OE, which is like diagonal. Well, this is also equal to kind of by what I wrote up here. This is just over. This is just the associated bundle of U intersect U prime over the flag. Okay. So now we try to do convolution with respect to this. So I'm sorry that like when it comes to like sheaves and these operations, I'm a little hand wavy, but this one?
Like when you solve them.
So people see both.
Oh, yes. Totally forgot, yes.
So that's a better display.
Yeah.
About to clarify.
Yes.
So you take U and U prime to be two different things. Is this supposed to still act on X, the form with XU or?
It's supposed to act on this direct sum. So
Oh, I see.
so it will take
It'll give you some.
yeah. So it's really like a kind of matrix multiplication, I guess.
Sure.
Like yeah. I'll do the quiver later and then we'll see. So what happens now is that convolution. So convolution by R U prime, which is pi inverse of the diagonal orbit. So let's draw the same picture that Mingzi draw last time. So we get something like U prime, P U prime, X U prime, E U X U. Up here is pi inverse of OE, which is X U intersect U prime. This is inclusion. Let me say, wait, no. Okay. Sorry. Yes.
X.
What is G and what is F?
Is it X or like the parabolic version?
This is no parabolic yet, because
Oh, yeah.
we're still on the E, like the
So
E orbit.
what's this map? X U intersect U prime to X.
Oh, this one doesn't exist.
Yes. Why does the top one exist?
Oh, this one, I mean, this one I take like because on the it's like a diagonal. So this is like G mod B V.
This is the bundle over there. The sex is there.
Yeah.
Okay.
Okay. I'm gonna do my best at this point. So we want I think like last time. So this one is so the top is a fiber product. Well, I guess that part doesn't matter yet. We want to for any what you call these, like O sub or like pi inverse of O sub W pi sub U pi sub U prime pi sub I don't know prime U of W. This is U prime.
Not all of them.
Well, I'm denoting like some some class in the some class in this G equivariant. I don't know if there's a better way. Maybe I'll just
No, and then are you trying
maybe I'll
to
just do like abstract notation, like a I don't know,
Yeah, just
like X
alpha.
alpha. Yeah, that's better. Sorry. Do G pullback and then X push forward of alpha. So I think oh no, but I do want to like kind of identify them via like kind of like to say like this is like sim P. Yeah.
Yeah, I guess they're just, because you already use OW for those things.
Yeah.
I think I call it PW or something. It's
Let-
like
let's say this is alpha, and then I want to say like I U prime pullback alpha, because I guess like I kind of want to unify how to identify kind of identify like these like bundles versus like the versus the cohomology on the like on the flag, which is like by pullback by like pi, pullback by pi, yeah. So this is like this becomes like pull back right here and pull back right here. So these two pull back for this this triangle. So I'm pretty sure these two pull back will give me the same pullback by like this like high triangle that I wrote. I want to identify like what did I do? In the end, should be I'll just give the ending here first. Or like what's expected to happen like F Euler characteristic of like normal, I think. And you intersect U prime in and U times F, which is the product of characters of U mod U intersect U prime times F. Yeah, sorry, I'll come back to this calculation later. But it's supposed to be it should be like a pullback by I and like a push forward by I, like somewhere in there. But I
How did we, why homology of X U prime is also polynomials in T star? How did we?
I guess it's like
this?
it's like Tom isomorphism, right? At least I know it's true for like K theory.
This vector bundle over.
Yeah. Yeah. Does this not hold?
Oh,
Yeah,
okay.
because this one.
Yeah.
So okay, so anyway, so here's like our first class of generators. This is RU primes. So what we see is that they kind of like take us from like one XU to another XU prime, right? So they kind of like go across these. Okay, I'm gonna move. So now I'll give the second class of I'm going to give the another kind of generators. So well, another kind of elements. Call them psi I, comma U maybe in HG homology of XU tensor XU. So these are same U's. Okay, so if U is Pi, so this is like the parabolic. If you add like the like a a sub I like weighted roots or like weighted elements to the Borel, Pi invariant. If U is P sub I invariant, this is same as this is same as in the no-Haeckel algebra that Maisie did for us last time. So like sigma I acting on F will be Si acting on F minus F over alpha sub I. Because or this is, oh sorry, I didn't even say like what this is supposed to be. This is supposed to be the class of I inverse of O closed sub Si. Right, so this is another orbit. Then, well, acting by convolution. So what does this look like? I G so the associated PI vector bundle of U. Okay, that's good. So it'll end up being the exact same thing that Mingzi did. And then we get the same sort of Demazor operator on these Fs. But if U is not the I invariant, we can't do this for reasons I don't understand. I mean, I know that I cannot like make that graph because like there'll be nothing to put down here, but otherwise I don't understand why I cannot do this. But it said that I cannot, so I have to do this. Let
Like vector bundle will be smaller like this.
Hmm?
I mean, vector bundle will be different right here, right? So like the bundles. It will intersect W.
yeah.
It's a sign variant. It's U and it's not a sign variant. It's
Sorry, what would not be SIS? What would not be
you
equivalent?
have this vector, this subspace. If it's a sign variant, intersection is U. If it's not a sign variant, the intersection is something else.
Okay. Why is that bad?
I don't know. Yeah.
Okay, yeah. I need to. If anyone knows, please tell me. Thank you. So let I think the notation is W sub I to be PI times U. Okay, so now this is PI invariant. Okay, and do so we have the R that we had before. So we from so we do WIU times psi I comma U. Yeah. Sure, let's do right. Times psi I comma U times R U WI. Yeah. So that will kind of bring us to like that will bring us back here. Because like this one will live in like HG star WI times U. And this one's like WI times WI, and this one's like U times WI, so we're back. And these are the two generators. So we have like this class of, so we have these sides that kind of like stay in each respective, like, I guess like endomorphisms. And then we have those like R's that kind of like jump around, like different ones. So question is, do they generate everything? Ben Webster didn't really go into it either. They say like if you make like S big enough somehow it will, but that's all I can say about that for now. Yeah, sorry.
Here you only have you
Where? Yeah. This one, same use. Yeah, so I guess I gave you two classes of like generators for this algebra. So these sides are like endomorphisms, kind of, and then like those R's, they go from, you can go from like one vector space to another vector space.
they together.
That's what I said. I don't know.
You don't know.
Yeah. They like it said that like if it's big enough somehow, whatever that means, like it does. But yeah,
If one is
like this like set S. Yeah, I guess it depends on what S is, but like I don't know, Ben Webster didn't go into it either much. So yeah, sorry. I'll-
Don't worry, but in the example you're asking about, you're just doing stuff with polynomials. Like both iterations that you just described. Yeah, I mean, not like this psi that is defined in the nice case, it's the Mysore operator, and this R is
It's multi-
this just like a product of like
Yeah,
linear things. But,
Yeah.
Yeah, then
if you pass to like I mean if you pass to like the fraction field of like sim t star, then yes, it generates. So that's nice.
no, I just there was this example where dimensional codimension was one, and like if dimensional codimension is one, you just like multiply by one by one element. So it shouldn't be too bad.
Yeah,
It's
yeah. I'll do some examples.
Yeah.
Okay, so we're back to growth indeed. Springer resolution. So okay, so what we had was n to be g, adjoint action. And then like u is b. Then we want to look at okay, yeah. These side eyes. So okay, so we want to look at like in H star sub G X sub U cross X sub U. Okay, so firstly, well, U equals B is not P sub I invariant. So we take E sub I acting on B, which I believe should be like B plus this this linear part, like the root subspace that minus AI weight. Let's call this E sub I. Okay, then we have then we consider action of, as I mentioned before, so we do R P sub I B psi, let's call it psi I. There's only one U, so no need to distinguish. But we also could times R B P sub I. Okay, so if we have this like act on some F, this is
Sorry, actually it's U, so first iteration, like if you act on this things, it's you start from H star U, go to H star W I, should be psi I W I.
sorry.
Yeah, and then that's the thing to repeat because of what's written above.
Yes, sorry. Thank you. Well, E sub I mod E sub I intersect B is just this this subspace mod. Well, it's just this subspace, I guess. Like so has character negative alpha I. Okay, and then this one is the Demazor operator we know and love. Si acting on minus alpha I F minus alpha I F over alpha I. Let me just rewrite that real quick. So Si act on alpha I is positive. So that gives me positive alpha I times SIF plus alpha IF. And then well, the alpha i's just kind of go away. And then this one, well, this one is what? B mod B intersect P sub I, which is well, P sub I contains B, so this is just I guess trivial character. So I get Si plus 1 F is the action of this whole thing. P sub I B psi I. Yeah.
So could you maybe write psi I W I
Sorry.
and say that it's action of psi I. Sorry, it's action I instead of the action of psi I U or B or whatever notation. Like we define I would yeah, you just define psi I as like psi I as this composition. So this is what you try to compute.
So now this is so this is I guess it like it acts on like HGXU. Yeah. This way. I read somewhere like this is like smash product, like something like alpha and wild. Yeah. And anyways, moving on. Okay, it's the KLR algebra time, like quiver representation time. To be a little hard, I'm gonna do my best. So this is where we'll see the KLR algebra. Okay, so this is our setup. Fix a quiver. Don't do self loops. I tried and I failed. Okay, and then for ijk, for each vertex I, fix like a dimension of that vertex, so to speak. I don't know, so like this one is like BI is like 3, BJ is 1, BK is 2 or something. Then let our G be the product of GL BI, and be the space of quiver representations, which is there are some of C or over edges. C from the tail of an edge to C or V sub the tail of the edge, like V sub head of an edge. So it's like a, I don't know, like three, like from like C3 to C1, depending on like the dimension we label them by. Okay, so yeah, it's just gonna be another instance of what we were doing. Now what? Right. Oh yeah, so G acting on like N by post compose by G and precomposed by G inverse. Yes. Okay, so my torus looks something like this, right? Like let's say TI1, TI2, TI3, or like TJ1, and then like I don't know, like TK1, TK2, right? Okay, so remember from like way back, I said that to define a B stable subspace, I take some like T such that alpha I of T is always greater than 0, i.e. for us, like sorry, gamma, stick to the same thing. So we want TI1 to be less than TI2 to be less than TI3, and then like TJ1, well, there's just one, and like TK1 less than TK2. Yeah, I guess now we're taking like this Borel to be like the Borel, I guess. Don't know why. They just chose to do that. Okay, so okay, so let's say like if if we can look at this and think of this as like setting like I to J, this is like, I don't know, like I to K. At least this helps me, I find. J to K, etc. So what does it mean for, so if I consider like, I don't know, like if this matrix and then like this entry is 1, like this matrix, what does it mean for this to be like positive? What am I saying?
I don't think it's an element of I. Maybe there's just element of different spaces. T is a subset of G, which is like block diagonal, and you are writing element of N, which is just like a large block matrix, but they belong to different sets, and maybe it can be confusing.
I think I know them. I think I understand now. So okay, so I can specify, so I can write a sequence like I bar is like, I don't know, like I, K, I, K. So like 3 I's, 1 J, 2 K's. This will specify this will specify like a U sub gamma in N. I guess the idea is that like, okay, if I take like this matrix and then like if I have like when I take like this matrix where like I have like an element like 1 here, when is like action by this gamma positive? It's when like this one, it's when like this one minus this one is positive. So like if like this one is like bigger than this one. Yeah, gamma's it's some torus element I picked, or like some co-root I picked, such that like these have these like inequalities.
Gamma is Ti1 dot Ti2.
Yeah. You know, I'm gonna go straight to the point. So the point is, we have all these like, now we have all these like U sub like boldface I, which is like so like these are indexed by like ways of sequencing. In my case, like 3 I's, 1 J's, and 2 K's, for example.
Sorry, can you maybe, so in the sequence, the number of letters equals the dimension of the vertex and what, and how do you specify you?
So what I'm really saying is like so like I picked gamma such that this is like Ti1 is less than Ti2 is less than Tj1 is less than Tk1. It's the first occurrence. Less than Ti3 is less than Tk2. Right. And I claim that like this sequence like uniquely determines subs like a B-stable subset of N. Yeah. So now okay, so now all right, so now let's do this for I bar like a sequence like I don't know like I J K I K. I'm going to draw something like this, like okay, and then I'm gonna say like okay.
So then get like in the subsets, like something, some item.
Okay, let me play this. Okay, so let's say I have a let's say I have let's say I have an edge from I to j. Okay, so then okay, so for my example, like let's say like I is 2D and like j is 1D. So so N contains like space of like matrices, like C2 to like 2 to 1. So this, so I don't know, like I can look at like the subspace generated like this and like the subspace generated by this.
Could you back at that definition? It's a little hard to follow for me.
Khovanov was defined earlier as direct sum of weight spaces where the value of gamma on the weight is at least 0. Now we're trying to describe it in a more explicit terms.
It's like a special case of earlier.
Yeah.
And the role of this word, I underbar, is to specify the Kerr character, right?
Yes. Yeah.
Mhm.
Yeah. It's just that I claim that like, so this co-carries like this sequence of like scalars. It only is like how they're like greater and less into each other, like in this way. Yeah.
Because all of the weights are just differences of different.
Yeah.
Wow.
Because I like pre-compose by the inverse, so that's gonna give like a minus that, and then like post-compose by like the itself, which is gonna like be like positive, like times like what's in that row, I guess. That's the best I can do for now. Okay, we're almost there. I think for the rest of it, I'm just going to state things and not explain too much.
You can think of it as just that you use it to reorder your matrix, not caring about these blocks, and you just take lower triangular matrices. So you order vectors, like there are 6 base vectors, and like first less and second less, and there are 6 of them, I1, I2, J1, K1, I3, K2. You just take matrices that lower triangular in this space. This precisely means that there's like the way this gamma is pairing of weight with this gamma is also non-negative. So
Yeah, it's like refining partial order to a total order, somehow, right?
say it again?
Like refining partial order
Yeah,
from the
exactly.
blocks to a total.
Yes.
So okay. Okay. I want to so I'm just going to draw something like this. I have some like order like I and then if I have like a dot like here, I'm gonna like call this like y2 and like c y1 y6, for example. Maybe the other way is better. Um, and then like if I have like this is like I and this is I, so they're like the same sequences. And then this one's and then like these neighboring ones are like labeled by i's and like crossed like this. This is kind of like the gamma I, and then like this denotes the sequence I. Yeah. I guess I look at I see this as like acting upon uh like C's generated by these like just if I just have dots. And I look at that as like the ring of polynomials. And then another class of things I have is like if I have like ij here, and this is like and like j I here. Let's call this like I and if I cross different strands, this is like the R I this plays the role like this element in the generalized Springer. So if I make these assignments, then I get like these relations. Which I'm gonna write out. So or like so and then like what we could do is like kind of like copy down like what the action was like before, like when acting on like F to be something like, so for example this one would be like the Mazur operation. Yeah, etc. And then and then
K
if
is the
you
position of the strand.
sorry,
K is the position of.
yeah, position K plus 1. Sorry, yeah. So then what happens is that if you just copy down exactly what we did like with the like how these R's and the size act by like either multiplying by character or like multiplying by character or the Demazor operator, we get these like pictorial relationships I'm gonna draw for you right now. This one's I and this one's J equals sorry, this is a cramp, so I'm gonna erase some things.
Yes.
Yeah, it's almost done, so I'm just gonna stay here.
Yeah.
And so you get the KLR algebra from the generalized Springer if you in this quiver ref example. Thank you.
Any questions?
What's the role of the difference between J and K and the indices in different blocks?
Like the sequence?
Yeah.
Okay, I'm gonna do my best to explain this. So okay, I take this.
I mean the role in the algebra or the action. Because I can see like the difference between those two in different blocks.
Which two, sorry?
So like
Yeah, maybe it's a good idea to say that there are like three objects. First is convolution algebra of I mean the sum of like this sum of homologies which has convolution structure. Then there is its action on polynomials on the sum of this h stars of x like xu, which is a bunch of polynomials, and what yes, and this like pictorial algebra.
Yeah.
Three objects are all visible.
Yeah.
As I understand this.
Yeah, exactly. So I guess like the I underline and like the I prime underline that stands for like graphs with like the bottom sequence is that one and like the top sequence is this one. Like all of these graphs. Yeah. And then I guess they act on like they act on like something like this. Like if we take like the right sum of sequences. Yeah, and then well with like think of this as like polynomial. Yeah.
So you think it's a polynomial when the strands are variables and the dots are the roots?
Yeah.
so you look down relations, but are those generic?
Yes.
And you said earlier the general construction in the but here it is.
So in this case, well that's what they say. If you want to, I mean you can ask like this I is, I guess in this when two i's are next to each other, it's like p like this like representation is pi invariant. For I can take a long time to prove this, but if I like if like maybe like I don't know like I k and like I k plus one are like in different places, then you have to like pass to a like you have to like bring this one here and then cross them and then bring this one out, which is like the r psi r that we did. Yeah.
So I guess you can compute the section of Mars explicitly just by computing the intersections of U intersecting prime and compute the vector and its characters. I mean, it sounds doable.
Yeah.
This number of for my so it's just one dimension from each of the edges. So edge from I to J gives exactly one matrix element which changes, and change line changes in other direction, so it's exactly the relation that line just erased. That the product of two bars collect this. No, it's well,
Oh, okay.
you just collect a bunch of these things.
So to go from like two different sequences, here you can just, it's enough to like do these R corresponding to like simple reflections. Like the character, I guess what I'm saying, you don't project the product of character thing, like, can you do it
Does
just one at a time and then?
Yeah. I guess that's the claim. That I didn't really prove. But yeah. You'll take like kind of like the minimal
Right.
way to cross over there.
Any Zoom questions? Okay, well,
Yeah, thanks, Larry. That was great.
Thank you.
okay, let's think.